Okay, this is the problem which you want to solve. So what's given here? So you need to find the specific volume of a superheated water. So if it's a superheated water vapor, the pressure is given 3.5 megapascal. The temperature is given 450 degrees centigrade based on ideal gas equation, the generalized compressibility chart, and then steam table. Determine the error involved in the first two cases. Okay, so we want to solve this problem using all these three methods, and the best the exact value would be found from this STEM table, right? So we'll try to find the error based on what you get from this STEM table. Let's try to start this with the ideal gas equation. So I think it should be easy for ideal gas equation because um, the PV is RT, right? And it says superheated water. And for superheated water, so you have water here, okay? So you this is table A1. You can find the value of gas constant. So this gas constant can be found from here. Pressure is given, which is 3.5 megapascal. Convert to Pascal. So it would be 3.5 multiplied by 10 to the power 6. And then temperature is given 450 degrees centigrade. Remember, it has to be always absolute temperature. Since you are doing this problem in SI unit system, you convert this to Kelvin. So if you add plus 273, you get temperature in Kelvin. Okay, so the only unknown is the specific volume. So this is how you can find the specific volume using the ideal gas equation. Okay, so pressure is given, always convert to basic unit. Temperature has to be in Kelvin. um, so this is the equation. So pressure is known, temperature is known in Kelvin, and R value you get from table A1 for water. Again, you need to convert this to again basic unit. If you see here it's kilojoule, so convert this kilojoule to joule by multiplying with 1000. So this becomes 461.5 joule per kg per Kelvin. It's a little bit complicated if you do not change the unit because everything needs to be cancelled out. So my suggestion is, especially when you use this ideal gas equation, convert everything to basic unit, kilojoule to joule, kilo pressure, kilopascal to Pascal, Newton, or Newton per meter square. So please do that conversion so that you don't have to worry about the units at the end. So we have everything to calculate the specific volume. That is only the unknown. So this one is the pressure in Pascal or Newton per meter square. So this is the value of R, which you got from appendix A1 in joule per kg per Kelvin. Okay, and again, very important, the temperature has to be always absolute temperature scale. Since you are doing SI unit, it has to be in Kelvin. It has to be in Kelvin. So that is only the unknown. So we just do the calculation. So it should be easy. So this is one way of solving using the ideal gas equation. Now let's move on to um, the next method, which is generalized compressibility chart. Okay, that's what we are going to use. Again, here the pressure and temperature is given. See, again, our process for finding a specific volume is, um, if you think about chart 815, you have reduced pressure on the x-axis, and then I think the reduced temperature, this is what it looks like. So these are reduced temperature, and this is the value of G. So if the pressure and temperature is given, then again we try to make use of this equation. So in this case, our goal is to find G. In order to find that, first calculate the reduced pressure, which is P by P critical, and reduced temperature, which is T by T critical. And these T critical and P critical values you get again from table A1. So the values are given here for steam. So the values are here. So once you know that, we can find out P critical and T critical. Now whatever it fits, based on the P critical and T critical value, you can find the value of G, and again put it into this equation and get the value. So that should be the process which you need to follow. Okay, so again, three options for generalized compressibility chart. And in this case, pressure and temperature given, you need to find the specific volume, right? So for that, you need to calculate the pressure reduced and temperature reduced. Once you know this critical temperature value which you get from appendix A1, and once you know that, get the value of G, and then put it into this equation. The only unknown is specific volume, and that's how you get the value of a specific volume. Okay, so this is the chart, which will be again, this is kind of, it's kind of zoomed here from 1 to from 0 to 1. Okay, so if the value of P reduces close to 0 to 1, then you better make use of this one because you get more accurate value. Okay, so this is x-axis is P reduce. See, you see something like this, these are like T reduce. You have to understand that. See, it moves this way, so you need to move along that. And then you see this line, these are V reduce, and then this is G. So in this case, since pressure and temperature is given, we try to find the G value, and once you know that, you make use of the ideal gas equation with the compressibility chart to find the specific volume. For water, the gas constant is given here, and critical property pressure and temperature is given here in table A1. So we should know where these properties values can be found. All right, so ready to go. Pressure given, temperature given. That's the equation we want to use. And R value, again, as I said before, you can get from the A1. So pre-critical, T-critical value you get from table A1. Now find the value of reduced pressure and temperature. You could, I think you better make use of A15 rather than this, because in the exam that's what you'll be using, not this one. It doesn't have the V reduce, but in this problem there is no we don't need V reduce. You can still use it, but from exam point of view, you can use A15. This is more clear, so that's why for explanation I am using this figure. Okay, so so P reduce is the value of P is given here, this divided by P critical. You could take the ratio, but the unit of this one and this one has to be the same. If you do megapascal for both, must be megapascal, but don't do one as Newton per meter square and other as megapascal. That's very, very important. Okay, both needs to have the same unit and the unit will cancel out. For T critical, again, it has to be always absolute. You can't say this is in degree centigrade, this is in degree centigrade. Absolutely wrong. It has to be always absolute temperature scale. Since we are doing in SI unit system, it has to be Kelvin. It has to be Kelvin. Okay, so this is the value you get for 0.15. So the reduced pressure is in x-axis, so it's somewhere pretty close to this here, this point, right? And reduced temperature is 1.11. See here, where is 1.11? This is 1.2, this is 1. So pretty very close to this one. So you can say somewhere the intersection point here, and then corresponding to that you get the value of Z. So that's the goal. We want to find the value of Z. So corresponding that, it's pretty close to 0.96. Again, from exam point of view, it doesn't have to be exact. Even if you get 0.9, it's okay because it's kind of visual. Okay, we're just visualizing the graph and trying to get the value. So if you get a little bit of variation, it's still okay when you do the homework or from exam point of view, because it's a graphical visualization by which you get the value of data. Now we have everything to calculate the value of a specific volume. Okay, so we know this big thing. Pressure is given, temperature is given, R you get from A1, and the value is 0.091519 meter cube per kg. So this is the second method, and third method is the most accurate method, and which we know before using the steam table. It already said is a superheated water. Remember, the ideal gas equation and an ideal gas equation with the compressibility chart can only be used for gas, not for liquid, not for solid. It has to be superheated vapor, and we know the situation in which we can apply low pressure, high temperature, um, if for the ideal gas equation. If not, then we have to either use modification with the compressibility chart, or we can use this steam table. So this steam table is the most accurate one. So the good thing is superheated water vapor is already given, so it's a superheated. You can look at the superheated table. In the superheated table, pressure and temperature are independent, they are not interrelated, so you need to look at 3.5 megapascal, which is here, and temperature is 450, is here. We are interested in finding the specific volume, so this is volume, specific volume here, so the value is here. So from A6 for superheated steam, this is the value. Now we have values from all these three methods. Now this is the most accurate one, right, using the steam table, property table. Now you can find the error, like this minus this divided by this would give you the error associated there for error 1. So you notice how much deviation from this one and with respect to this value, and it's 3.65%, not much. See, we are getting less as compared to ideal gas. In ideal gas equation you have like pretty close to 4%, but for compressibility chart the error is very small, which is 0.5%, right? So that's why the ideal gas equation with the compressibility chart is better, the representation of the accurate value.